Yeah, I said. Is it visible?
Yes.
Okay.
Sir, ఒక్క నిమిషం.
Madam, is it possible to move for the next slide? Madam?
Is it okay?
Yes, okay, madam.
Yeah, actually,
Go for the next slide, madam.
It's not a yes. Tell me.
It's going for the next slide. We'll check them, madam. Second slide. Okay, madam. It's very good, madam.
Yeah, it's we usually take our class in IIT Roorkee using Microsoft Teams.
Okay, madam. Thank you, madam.
Madam,
start the session.
Yeah, you can start, please.
Okay. It's dear participants, it's very good morning. It's the second day of our ACT sponsored STTP program for Series 3. Today, our resource person, Dr. Premila Jana at IIT Roorkee. Dr. Premila, madam, please introduce today our resource persons.
Dear participants, good morning to all of you. Now I am going to introduce Dr. Premalata Jaina, today's speaker. Dr. Premalata Jaina received the BTech degree in Electrical Engineering from Utkal University, Odisha, India in 2001. MTech degree in Power System Engineering, IIT Kharagpur in 2006. And PhD degree in Power System Engineering, IIT Kharagpur 2011. She worked as an assistant professor in IIT Roorkee since 2012. Currently, she is working as an associate professor in IIT Roorkee. Her research interests include power system protection, microgrid issues to the Women Excellence Award 2017 from DST, New Delhi. The Younger Engineer Award, Indian National Academy of Engineering, and the POSOCO Power System Award, Power Grid Corporation of India Limited in 2013. Now, ma'am is going to give her talk on novel protection schemes for smart grid protection. Ma'am, you please start your session, ma'am.
Okay, thank you so much for the introduction. In fact, every time I say it is not required. So if I could see the videos, it will be good for me because while we deliver the lectures, so if video will be on, so we can at least will be motivated to present nicely. So I request to the participants as much as possible if you could switch on your videos, and so that we can interact and we can go ahead properly. So is it possible, sir?
Yes, it is possible, madam.
Yeah, so you can tell the participants they can switch on the videos and they can interrupt me. Yeah.
Dear participants, those who are interested to turn on your video also, because the resource person willing to interact with online also. Maybe see your face means you are motivated and large.
The class will be more live.
It's like our class.
So it's a basically a very informal discussion with all the participants and me and organizers.
Another one, madam, many of them are used for the mobile net. Suppose if we turn on the video means maybe the internet connectivity problem will arise. In this reason, many of the participants, I think it's not turned on their video also.
No issue.
Okay, madam. Thank you.
So madam, now today's again I thanks to organizers and college for inviting me. So I'll put my best effort to just inform some and discuss some novel protection schemes which we have developed in IIT Roorkee. I mean in our laboratory at IIT Roorkee, Smart Grid Laboratories. So our research initiatives I can discuss with all of you, and of course if you have some discussions and queries, you are always welcome. So as you know, one of the lecture I have taken also with professor. So he has invited me. That time I was discussing the introduction to smart grid, that why this smart grid is very essential, and what are the key factors which helps us, like which drive us to move ahead towards the smart grid era. But however, even though we are dreaming, or we are just trying to implement, or we are just trying to live in the smart grid environment and to make our existing grid smarter enough, but at the same time there are so many disadvantages, or say not, rather I can say, so many you have stability issues, you have power quality issues, you have protection issues, then you have like other like converter design topology, its reaction, like designing the solar, wind, battery, so many aspects are available. The challenging issues are there in smart grid environment. So in that sense, out of it, protection is one of the major issues in smart grid area, and which we are taking over, and mostly like 12-13 students are working with me, and MTechs and PhD and BTech students also, they are working with me. Moving ahead, so these are my outlines. Like I'll just talk about protection issues in microgrid, and then anti-aligning detection issues. Then anti-aligning detection issues, techniques, then adaptive protection schemes. If time permits, I can go for work-related coordination, and some research works which were carrying out in IIT Roorkee, so I'll discuss. So these are some of the points I am just going to discuss. So what are the for this smart grid, what is the motivation? So the major motivation is we have to reduce the carbon dioxide emission, and we have to reduce the global warming, and also we have to fulfill the peak energy deficit. So therefore, the renewable sources are the alternative ways out, so to fulfill these requirements. And so out of it, if you see, the key renewable sources in India are wind and solar. So by 2022, we are just planning to install like 100 gigawatt of solar and 60 gigawatt of wind. And not only this, you can see that there is also one more information. By 2030, we are going to install around 300 gigawatt of renewable energy sources to our existing network. So renewable sources which the energy as well. Otherwise, there will be some efficient operation of the renewable sources may not happen. So therefore, storage is very essential. And so integration of storage and then intermittent nature of the renewable sources together, like these sources bring a big challenging issue towards the protection of the smart grid or existing network where the renewable sources are integrated. So if we're going to integrate 30 gigawatt of renewable sources, so it is a big task for all of us. So therefore, many researchers and many industry people, so they are just tying up their hands and bringing some pilot projects, and they are executing the test beds, and they are just testing their proposed innovative techniques, so in different areas. So it is therefore, this is one of the major research area, and this is also essential for all of us to investigate what are the ways and possibilities. Now, so going ahead, like this is small bed of like microgrid, where you can see my cursor. This is my main grid, and this is my connecting transformer, which connects the rest of the microgrid network. And this is actually this loop maze type microgrid. It is not a radial. So mostly my this presentation is limited to distribution type of network. And so I'm not going to talk about like high voltage. It's a low voltage AC microgrid system. So
Sorry to interrupt, madam.
yeah,
Good morning,
please.
madam.
Yeah.
Can you put in full screen mode, madam?
Okay, fine. So
PPT, madam. Yes.
yeah, is it fine now?
Okay. Yes, madam. Good.
Yeah.
Thank you, madam.
Okay, thank you. So now, so in this context, I'll just talk about the protection aspects for AC microgrid. Okay, so this we have also DC microgrid, we have AC microgrid, we have hybrid microgrid. Means hybrid means both AC and DC are interconnected through a bidirectional converter. So, but I'll not talk about this DC or hybrid. So I'll talk about the AC microgrid system. Now, if you see in this particular picture, this is our grid and this is the connecting transformer, and this point where the rest of the network is connected, and this point is known as point of common coupling. So just where my microgrid starts connecting to the main grid. Okay, so that point itself is known as point of common coupling. Now you could see this rest of the maze type. It's a maze type network, right? It's not a radial network. And you may be astonished why I said that it is, I'm just limited to low voltage AC microgrid system. There are certain reasons. I mean, of course, there are various reasons. I can say two of them or three of them. There are so many other reasons. Like planning that grids have northeast grid, western grid, southern grid. So if I'm aiming to make our network smart, I'm not going to that part. I hope all of you who have attended my previous lecture, which has been coordinated by Professor. So then you can refer to that videos maybe. So there we have discussed very deeply that what is the need of this smaller portion, smaller microgrid system. As the name is, it is written here micro. I mean, suddenly I just came back. From smart grid to microgrid. That discussion has been conducted in that particular session. But still, I'll give you some sort of thought process on that. So micro. Exactly our grid capacity is in the range of gigawatt. But in microgrid, if we'll multiply, micro means 10 to the power minus 6 with 10 to the power 9. So it will be in the range of kilowatt or some megawatt. So we are trying to reduce the losses while we are transmitting the power from one generating station to the load terminal. So we have to travel some kilometers of distance, maybe 1,000 kilometers, maybe 400 kilometers, maybe 200 kilometers. So why will just waste our power? So in terms of line losses. So to avoid that, the very important, very immediate, arrangement you can say in smart grid environment is the microgrid system. So this microgrid system is a smaller grid which has a capability of handling power up to 50 megawatt. But now it is in IEEE standard. It is designed that it can also handle up to 100 megawatt. But fortunately, or you can say in a very better sense, like we can go up to 50 megawatt, maybe lesser than that. So, small chunk of power bulk point where you have your loads are basically getting the power supply close to their periphery, near to that. You have the solar park, you have the wind park, you have the storage facility. So the load can easily enjoy the reliability, efficient and sustainable supply, right? So in that way, what we are doing it that the load and the utilities, they can basically they can communicate in both the ways, like in terms of like power flow as well as their data information exchange. Okay, so otherwise, if there will be some outage, earlier cases like conventional grids, and it will take a longer time, like some hours, maybe some days, some months also. So to avoid it, the small been divided into smaller northern grid. If we can mix different areas of microgrids together, so that those kind of arrangement is known as networked microgrid. You can write it also. The networked microgrid means there are so many microgrids are connected together and as a whole, so they will just make the final smart grid environment. So there is a question also sometimes we people ask like we interact whether every microgrid is a smart grid or every smart grid is a microgrid. Yeah, every microgrid not necessarily just smart grid, but of course it's a part of the smart grid environment. And if you just make it fully automated and the features which are actually required for smart grid, so if it is present within that microgrid, of course it's a smart grid. Okay, so in that way you can learn more. So this is actually the microgrid bed. We have like so here's fuel cell inverters. Like this is actually the battery storage, and this battery output is DC. So this DC to AC converter it is, okay, and it converts AC, and this AC is connected to the AC bus. And here you have fuel cell, and this fuel cell has also one inverter, which the fuel cell output is basically DC, and it converts DC to AC also. And here we have micro turbine, and this is a connecting transformer. And why this connecting transformer is present if the voltage level is not equal to the this ring main or mesh network of my AC low voltage distribution network. So in that sense we have to step up the voltage. Mostly it is step up transformers, and these transformers known as connecting transformers. And this is micro hydro, like small hydro power plants, and then you have biomass PV. Then PV also the output is basically DC, and so therefore we need one inverter, and from the using this inverter, this DC is going to convert it to AC, and that AC is connected to my AC bus. Similarly, we have DFIG. DFIG stands for W-fed induction generator, and this is actually one wind generating station. And basically initially the wind farm generates AC, and that AC is converted to DC, and then DC is further converted to AC, and it is connected to the AC bus. And then of course this one, the last one, is a diesel generator set. This is actually the backup. It is not a renewable source of this microgrid system, but however the diesel generator set is the it acts like a what? It acts like a backup generator. So this is for our understanding. You have also loads over here, and also we have the battery storage, and as well as we have also the grid conventional. The conventional grid we understand this manner, and so apart from that, in the microgrid, this one cursor you can see, this is your microgrid. So this microgrid can operate in a grid connected mode, or either it can operate in an islanded mode. So what is the meaning of grid connected mode of operation? When the grid is connected, so this is actually known as the grid side circuit breaker and grid side connecting transformer, main transformer, which steps up. I mean, sometimes it's step down. This is a step down transformer. If my grid is of 33 kV and this particular network, mesh network, is 11 kV, so this transformer is going to be a step down transformer, and which will step down the 33 kV voltage level to the 11 kV voltage level. So in this way, the actual real, I can show you in my talk process also some realistic network and some IEEE standard network. So what I'm talking right now, so I'm just considering one 11 kV substation, or maximum to maximum 4.16 kV substations are network, a low voltage AC network. So where the solar, wind, all renewable sources, storage devices are present. So what do you think? So from here, can you just guess, like, just you forget all the renewable sources, storage, everything you just forget. Simply you have a grid, okay? So the grid is here, and you have some loads over there. So obviously the existing technology, existing protection philosophy, what was present earlier before the embedment or reconnection and connection of the renewable sources. See, so those settings and those philosophy, those technology and innovations are obviously different what we are going to I'm just going to talk to you, all of you. So with the presence of renewable sources, because there are so many reasons behind it. Why there is a change in philosophy and why it is so challenging. Now we can see that it is very clear. Sorry, the AC, low voltage AC distribution networks are very active in nature. They are not passive in nature. Rather, it was earlier, it was very passive in nature, but nowadays it is very active in nature. So those active facilities, like active networks, to handle, we have to definitely change the protection philosophy to great extent. So the conventional philosophy, protection philosophy, or even devices also you can take to account also. So those are going to be failed. So those are not going to work anymore, because I'll just show you some very important points. I'll just share with all of you. So from there you can understand that why those philosophies or technologies are going to be improved, or it should be replaced rather. So these are very important issues we have collected after reviewing many papers. So maybe, of course, the research is always unlimited. Research has no end. Even Einstein also, he said, I have collected one sand particle from the ocean of knowledge. So of course we are also, very in that sense, we are just starting scratch point. So there are so many research articles and research is going on in this direction. So we have collected a few articles, important articles from IEEE transactions, IEEE standards. So then we have taken off these issues. I can. So the second issue is bi-directional fault current. Third one is fault stripping, and the fourth one is blinding of protection. So let us understand each issues properly. Okay, so that it will be interesting. So I just said this topic, the title is dynamics in level of fault currents. So what is the meaning of that? Let us understand, then we can understand in some figurative form and figure we'll try to understand. So dynamics in level of fault currents, dynamics word itself means what? It is changing in nature. Static means it is constant. So dynamic means it is changing in nature with respect to time. Okay, so this dynamics in level of fault current means what? Just in layman word I can explain to all of you that if suppose our AC microgrid has some renewable sources and some batteries, or some, again also it has a grid. So then if any fault is incepted, any disturbance, like in protection, the main concept is the fault. So the fault is one of the major culprit which deteriorates, which takes a lot of money, and it destroys many valuable equipments. So this fault should be isolated and cleared as quick as possible. So that is what is the analysis. I'll just keep on trying to inform you my last 10-20 slides. So this fault, it's a disturbance which is actually undesirable event, which happens inside the network. It may be a smart network or it may be a conventional network, doesn't matter. The fault doesn't know whether it's a smart network or it's a conventional network. So the fault is inevitable nature also. Inevitable means it can come at any time. But honestly speaking, if the fault comes to picture in the network, so it destroys lot many things in terms of devices and monies and cost, so many things, person as well, life as well. So this fault, when fault will be inserted inside the network, so it drives, it gets, the path, the circuit will see huge amount of current, which is going to flow within the feeders or lines, and which will create lot many problems. So therefore this fault we have to detect, we have to isolate as quick as possible inside the AC microgrid system. So that is what is the main point here to discuss with all of you. So now this fault currents, the label of fault currents changes to time. It is obvious, because as I said, inside a AC microgrid system, we have many renewable sources and storage devices are connected together along with the main grid. So what will happen if any fault will occur? So the both, I mean, all the sources together will try to contribute some fault current to the fault point, because the point is, the fault point is the minimum voltage point. Where the fault occurs, the voltage dips at that point. Okay, so if the voltage sudden at that sort of, suppose see my picture here, the red one is my point. The fault is detected in this is load 1, this is load 2, and two renewable sources. DER stands for distributed renewable energy source, distributed energy source or resource. Okay, so this is my DER1 and this is my DER2. Now, if any fault occurs here, the fault is incepted here in this particular feeder or line, what will happen? This grid, my main grid also will try to supply some current. This renewable DER1 also will try to supply some current, and DER2 also will try to supply some current. So all the three sources in this small network, it's a radial network I have taken. So in this small radial network, there are three sources and two loads. Okay, so these three sources, the first source is the main grid, second source is the energy source I am talking, that is the renewable source 1, and this is renewable source 2. So all the three sources will try to push power at the current towards the fault point. This is the property of the network. Why? Because you know, it's a very basic concept for all of us. The power, the current flows from higher voltage terminal to lower voltage terminal. So when the voltage difference is between 2 points, from the higher voltage terminal to the lower voltage terminal, the current flows. It is a very simple philosophy, basic concept of our electrical network. So as I said to all of you that when the fault is incepted in any one of the feeder, so what will happen, this main grid is having this PCC point, this bus has higher voltage in comparison to the fault point voltage. As I said, the point where the fault is incepted, the voltage dips. So this voltage difference between the VPCC and V fault, there is a gap. So due to that, the current is going to be supplied by the main grid. And similarly, the voltage available at this DER1 terminal also higher than this fault point voltage. So similarly, the DER2. So now coming to this is one concept over here. And second, this coming to my title, dynamics in level of fault currents. So basically the dynamics means I can understand, I can just explain to you magnitude of the fault current. So as it is an AC network, AC microgrid, so we deal with mostly the magnitude of the fault current and the angle of the fault current. So this magnitude is basically, what is that? When we have some current, some instantaneous current waveform. So this instantaneous current waveform, by looking at it, you cannot say that what is the angle of that waveform of the current. So we have to either extract the phasors by some phasor estimation technique, and we have to tell what is the magnitude, what is the phase angle, like that. So I'm talking about here this capital I have written, that means, see, in electrical notation, we use small I as the instantaneous current and capital I as the phasor values, phasor current. Okay, so that's why it is here we have used GIGF. So what is IGF? This IGF is the fault current. G stands for grid, main grid, and F stands for fault. So this IGF is the current, main fault current contributed by the main grid to the fault point. And similarly, IG1F is the fault current contributed by this DER1, and IG2F is the fault current contributed by DER2. This due to this presence of DER2, what is the total fault current? IF. This IF is nothing, IGF plus IG1F plus IG2F. So the addition of all the three fault currents which are contributed by the three sources. But remember, if suppose your DR1, DR2 are not present, so what is your IF? IF is equal to simply I capital GF. Simply the fault current is equal to the fault current contributed by the main grid. Okay, so now this first figure is known as the grid connected mode. I said from the beginning of this microgrid, I said that the microgrid can operate either in grid connected mode or it can operate in islanded mode. So this is grid connected mode. Why? Because this circuit breaker CB1, which is the main circuit breaker just near to the PCC, and this circuit breaker belongs to the periphery of the main grid substation. So this circuit breaker is closed here. So that means the rest of the network, this feeder which has renewable sources and loads, basically this acts like a small microgrid and which is connected to this main grid through this circuit breaker. If the circuit breaker opens, that means it is in islanded mode. If it is connected, then it is operating in a grid connected mode. It is like this. So in this operation grid connected mode, so this magnitude is quite high, isn't it? It is a combination of three currents. Now, if you could see here that in case of your islanded mode, means I have written here CB1 is open, means this breaker is open. So what will happen? Now your IF is equal to IG small 1 F and IG2 F. So that means your grid current is absent. Now this grid side IGF is 0. So therefore that means it is a small example I am just keeping in front of you, that to make you understand that what is the meaning of mathematically with the figures I explained to you, that what do you mean by dynamics in fault current. The dynamics means the fault current level changes time to time. And not only that, let us say in this, even in the islanded mode also, let us say your DER2 is switched off due to some reason. Let us say for maintenance purpose or some disturbance or some fault inside the components of the DER2. Anything can happen. So if the DER2 even absent, fault current, how? The fault current magnitude changes, even angle also to some extent. So angle as well as the magnitude changes depending on the mode of operation of the microgrid. And also there are two reasons why this dynamics changes. And the second one is the penetration of DER. So if you are penetrating the renewable sources to the existing grid or AC microgrid, low voltage smart grid, so then we are just indirectly we are modulating the current magnitude. Even for just forget the fault case. Suppose there is no fault, even there is no fault. Through this particular line, the pre-fault current also varies with the absence of DER, with the presence of DER also. So that means what I'm trying to say, the takeaway from this particular slide is, with the penetration of renewable sources and with the grid connected and islanded mode of operation, both the pre-fault and fault current magnitudes are modulated, are changed. Okay, so this is a very first important issue of smart grid network, where you have renewable sources, we have grids, we have storage devices. So going ahead and moving ahead, so this is the second issue, the bidirectional fault current. The first issue is the magnitude is changed. Now what about the direction of the fault current? That also changes. Even not only fault current direction, the pre-fault current direction also changes with the variation in the supply of the renewable sources like solar and wind, and of course the grid terminals and storage devices. So what is this meaning of bidirectional fault current in microgrid? This is your main grid. This is my circuit breaker, and this is one of the feeder which is originated from this main substation through this circuit breaker 2. The circuit breaker 1 belongs to this main grid, and circuit breaker 2 is basically protecting this particular feeder. And in this feeder we have three laterals, and this is one where one load is present. Here second load, here is one renewable source present. So we have taken these pictures to make understand this concept. I can also explain another circuit also after this. So if any fault, so this is a red color, this is a fault position. So there are two faults I have taken. One fault is F1. So let us talk about it first. So for this fault, the red color signs what I have kept here. one fault current is going to be contributed by this main grid. Current is going to contribute. The dotted lines which I have shown, these fault currents, fault current components are just basically from the main grid to the fault point. From left to right, with respect to me, it is from main grid to fault point. So in other sense also we can say, in electrical term and in smart grid we call it as the grid side we call as upstream side, and the other side just the from where the power is flowing from the towards the load is known as downstream side. So I mean the power flow decides from the terminal where the power originates is known as upstream, and the where the power goes, and that side is known as downstream. So the on the downstream side for understanding, because for me it is left right, for you it is right left, so therefore it is very important to take this word like convention like upstream downstream, it will be easier. So the main grid side is called as upstream and the other side is not downstream. So in the downstream side there is a fault which is incepted here, and the red colors are the currents you can see, they are coming from upstream to downstream side. But now let us say you create one more fault on the upstream side bus. This is a PCC bus, the green one. Okay, now for this green one fault point, the main grid fault current contribution direction remains as it is. But however, see, this DER current contribution is just reversed. It is coming, this green side is coming from downstream side to upstream side. So this is the direction change in the fault current. So this, therefore, see actually why it is happening, because now the fault position has been changed. So therefore the current will reverse its direction. Instead of flowing from upstream to downstream, it will flow from downstream to upstream. So this is known as bidirectional fault current, and during this process of reversing the direction of the fault, reversal process of the direction of the fault, the angle changes. Of course, the magnitude also will change, I'm not denying, but the angle is mostly affected. Almost 180-degree change will be there. And because you see here, I have very small component I have marked for your understanding. You could see this smaller this red one, this red arrow, small component, this is the direction. See, every circuit breaker, near to circuit breaker we have CT, and the CT will see the current direction in this direction from upstream downstream, and for this fault it will see in the opposite direction. So see, the direction totally changed. So in that sense what will happen, the polarity will change and the angle will also change. So this is how the penetration of DERs changes the direction of the fault, and the traditional, what will happen? So in this process, the directional, unidirectional overcurrent relays may find some limitation. So the third issue is the fault stripping. Okay, so fault stripping means you have like one very important. Hello, am I audible? Am I
Yes,
audible?
ma'am.
Yes, madam.
Yes,
Yes, madam.
Yeah, thank you so much. So this just a minute. Yeah, my PPT is visible to all of you.
Yes, madam.
Yeah. So this fault stripping is a third issue where you can see here the fault stripping means the word itself. You can understand that false means something is just missed or something is stripped without any reason. That is known as fault stripping. How is it how it is happening? So let us take this figure. This is my main grid and this is my main grid circuit breaker, and this is my PCC bus. And from this PCC bus, there are two feeders are originated. This is my feeder 1 and this is my feeder 2. So let us say here is one fault, and fault is always a danger signal, right? So fault, there is many of you have, I think you have seen in your home short circuit. So inside your home short circuit, so it's a very dangerous signal. So every time we call it as represent in red color. So this fault is incepted in this feeder 2. Now what will happen? In this process, you have also in this feeder 1, there are two feeders I said which are originated from this PCC, feeder 1 and feeder 2. So this feeder 1 has one DER connection, but in feeder 2 we have not shown that. For example, for explaining this, we have taken these pictures. So this feeder 1 is basically supplying some current to this fault point as well, because the DER will try to push some current, fault current to this fault point, and as well as the main grid also will try to push some current to that. Try to push some and supply some fault current to the fault point. In this process, what is happening? Let us analyze. So this feeder 1 is protected by one overcurrent relay. I'm just taking it example because in our general practice in distribution network, in even then it is a mesh network or it's a feeder by radial networks or whatever. So there the overcurrent relays are masterpiece. Overcurrent relays guard or protect the feeders. So this is let us say it's an overcurrent relay. And this, due to this fault inception, this DER will try to supply some fault current to this point. And as well as this red marks dotted line, the main grid also will try to supply some fault current. So in this process, relay R1, which is protecting feeder 1, and relay R2, overcurrent relay, which is protecting feeder 2, both of current, isn't it? R1 will current, R2 will also see some fault current. So what will happen? In this process, it is fine. So because the fault is in feeder 2, so we have to basically, with help of this R2, will sense that there is a fault in my feeder 2. So it will just give a trip signal to the circuit breaker, and it will open, the circuit breaker will open this feeder 2. But however, at the same time, R1 will not remain silent. It will also try to give a trip signal, because it will sense there is a fault, because it will not remain silent. So when the fault current magnitude will increase the set value, so the overcurrent relay reacts and it will generate one trip signal and the circuit breaker will open. So in this process, the feeder 1, which is in feeder 1, which is a healthy feeder, so it will be sacrificed. It will be fault stripped. So this process is known as fault stripping. So to give solutions, so this is one of the best challenging issue to how to give solution to this type of problem. So we have addressed some technique, innovative techniques, how to handle such kind of issues. Okay, so this is this fault stripping means stripping of healthy feeder, and of course when this healthy feeder is disconnected and this load L1 is going to be interrupted, and this load area, this is suppose one area. So as this breaker is open here, so this area will be under load shedding condition. So there will be no power supply, unnecessarily tripping of the lines, and loads will be disturbed. And the last issue I'll explain to all of you, the black
Yes, madam. Disconnected. Dear participants, I think it's a net problem in this resource person side. Please wait for 2 or 3 minutes. He will rejoin. Dear participants, wait for 5 minutes. Our team will communicate the resource person. Dear participants, it's a very good morning. Due to internet connectivity problem, the madam will connect through her mobile. It's take only for 2 to 3 minutes. She will rejoin. Sorry for this delay.
వాళ్ళ అబ్బాయి ఫోన్లో ఉంటాయి అడుగు, వాళ్ళ కొడుకు ఫోన్లో ఉండదు.
I'm extremely sorry because there is some internet issue in IT Roorkee, so it is showing problem. Is it audible? Am I audible to all of you? Is it visible my PPTs to all of you? Hello.
Yes, madam. Yes, madam.
Yeah, my PPT is visible to all of you.
Yes, madam.
Okay. So there is some internet issue. I'm extremely sorry for this interruption. Okay. So I joined through my mobile hotspot. So this is the fourth issue, the blinding of protection. Now this is the another major issue which has been handled by many researchers and they have published many papers. Even this is also going to be included in the patent of many companies also. This blinding issue is major issue. What is that? Suppose you have this main grid system and then this is one feeder and here one fault is created at this point, right? And due to this fault point, this main grid will also supply some current and this DER also will supply some current. So together the two faults are going to be contributed. So this kind of situation, I mean, uh, due to this, what will happen? Let us say your fault current remains constant because the fault path remains constant. Okay, so this fault current is a combination of the two fault current. One is by the grid and another one is by the DER. Resultant of this two fault currents is the total fault current. Now, let us say just you for the time being, you just think that there is no presence of DER. So that means the fault current, this I fault is equal to IGF, isn't it? The fault current contributed by the main grid. But now let us say now the DER is present, so the fault current will remain constant. Like let us say 10 ampere. 10 ampere earlier was contributed by only the grid, but now due to the presence of DER, this 10 ampere is going to be divided into two sources. The one source, let us say 8 ampere is going to be derived by the contributed by the main grid, and 2 ampere is going to be contributed by the DER. So this due to the division process at this relay location, the relay will see 8 ampere instead of 10 ampere. 10 ampere. That means the current magnitude will reduce at this location due to the presence of DER. So what will happen? So due to this DER presence, mostly this 8 ampere will 10 ampere will just the relay will see just like 8 ampere. So it may also sometimes fall. This is for example I'm just saying to you, and this magnitude may fall below the threshold as well, isn't it? So then the relay will not say that there is a fault, and the relay will not also generate any trip signal for opening the circuit breaker. So this is known as blinding. So blinding term itself here, the meaning is even though there is a fault, but the relay is not able to trip the line. So this concept is known as blinding. Okay, so these are the four major issues I just shared with all of you as far as the current magnitude, angle, directions, feeder positions are concerned. So there are so many other issues also. Along with that, one more issue I just want to share with all of you, that if the fault is inseparate in front of a solar based or inverter based renewable source, the renewable sources which are having in inverter interface, just like your fuel cell, just like your we have solar, we have batteries, we have biodiesel generators, kind of in front of those renewable sources, inverter based renewable sources, the fault current magnitude is automatically clamped to 2 per unit. Understand why? Because for the protection of the inverter devices, inside the inverter we have power electronics devices like IGBTs or GTOs or diodes. So to save those power electronics devices, there is a clamping circuit present. That the controller is also present, so that will try to clamp the current magnitude to 2 per unit. But if the same fault is inserted in front of a synchronous based renewable source, so what are those synchronous based renewable sources? Like small hydropower plants we have, so like diesel generators sets I have shown in the first figure of the microgrid, there is a diesel generator. So this those in diesel generator we have synchronous base generators. So in front of that, if the fault is incepted, then of course there is no inverter. So the fault current is not anymore clamped to per unit, 2 per unit. Rather, it is increased to 5 per unit or something, sometimes more than that also. So these are the concepts what I'm just sharing with all of you. We have reviewed like many papers, and I'm just presenting in front of you. So this is a very all the together the concept, 4 things what I have shown to all of you. Correct? So the 4 or 5 concept rather I can say, because 5th one I said with you that if the fault is incepted in front of the your inverter based renewable source, then what will happen? Then our thing will be different. Current magnitude will be 2 per unit. It will be clamped. The current magnitude will be clamped automatically with help of the inverters. But if the fault is created in front of the synchronous based renewable source, then it is going to be more many-folded. Okay, is it clear? So now let us take this picture where all the 5 scenarios are present together. This is my main grid, and this is feeder 1. This is line 1, which is protected by 2 relays, overcurrent relays R1 and R2. This is my feeder 1, and this is feeder 2. This feeder is also protected by 2 relays R3, R4, and this is a feeder 2, which is also protected by 2 relays R5 and R6. And at this bus, we have one renewable source, SBDR. SB stands for synchronous based distributed energy resource, and IBDR stands for inverter based distributed energy resource. Okay. Now, if let us say here is one fault is created at feeder 2. This is my feeder 1 and this is my feeder 2. So in feeder 2, there is a fault F which is incepted, shown here, this cross symbol. So what will happen? This grid will also try to supply some current. And this renewable source SBDR also will try to supply some fault current. And this IBDR also will try to supply some fault current. So all together, all the 3 sources will try to supply the fault current. This concept I explained from the very beginning, that the fault point is the lowest, the fault point has the lowest voltage magnitude. The voltage dips there. So therefore, whatever the sources are present inside that network, they will try to, they'll push the fault current to that point. So, so as a result, now the flow of fault currents through the relays in DN. So the DN means distribution network. So for fault point F, this F is my fault point. The grade 1 is the current contributed by the green grid, and this green one, the current is contributed by the SBDR, and the blue one fault component is contributed by the IBDR. So can you just explain what the points I have just shown to all of you? See what type of issues. Issues. The first issue, the dynamics in fault current. Which relay will see? Dynamics means the change in fault current label. This R5 will see. Why? Who will answer me? Can I ask a question to all of you with the permission of the organizer?
Carry on, madam. Madam, it's here. Your voice is audible. You carry on, madam.
Pardon?
Yes, madam, you ask the questions to participants. It's okay, no problem, madam. It's your session.
No.
You are the owner of this session.
The session should be interactive so that we will enjoy, isn't it? See, if I'll keep on talking, that doesn't look good, right?
Yes.
So
yes, madam.
So therefore, I have some, maybe in between I may ask some few questions. It is not a question actually. It's a discussion rather. So,
yes.
So now it's not at all question. Don't take another way. So we all are in the same platform. So now for fault point F, can you just say why the dynamics, the first issue was the dynamics in fault current, and second was, if I'm not wrong, direction change in fault current, third one fault stripping, and fourth one blinding in protection. So now the fault for this fault point F, the dynamics in fault current changes. Why? Who will answer this question? I mean this point. Yeah. You can open your video and you can talk to me.
Dear participants, please unmute your audio and interact with our resource person. It's somewhat more interactive.
Yeah. So can you just help me by saying, then I can confirm that you're listening to me. Otherwise, I'll just assume that you're not listening. Is it so?
Yes.
Yeah. So who will help me by answering that when this particular fault is there? So relay, I mean this R5 will be having dynamics or change in fault current level. Why? Yes. Will answer this point. Help me.
Dear participants, to unmute your audio. Just discuss and meet. So both of them, someone it's very happy. Madam also it's very happy.
Yeah, no issue. So if they maybe at the end they can ask, if they could not understand any point, they can also ask me at the end. I'll be answering. So for the time being, let me answer this. So for the fault point F, at this point, this relay or the device, protective device R5 is going to see dynamics in fault current. The meaning is this relay will see a change in current magnitude, because this relay is going to see two fault currents, isn't it? One fault current IF grid, the red one, and another fault current contribution, that is IF SVD, the green one. So these two are in the same direction. So in general, when the two phasors are two currents in the same direction, they are added, and when the two currents in the opposite direction, they are subtracted. So you may subtract or you may add, so it doesn't matter, but the current dynamics is going to be changed. Remember, the dynamics doesn't mean that the current magnitude will increase. It may also decrease. Sometimes the current flow may be in opposite direction. So in that case, the two phasors are going to be added but of course in a negative manner. So this R5 is having two components of the fault current, the red one and this green one. So if I'll ask what is the fault current seen by this R5, it is addition of IF grid plus IF SVD. If I'm not wrong, or you can interrupt me in between, if you could not understand or you could not just pick up the points, you can always interrupt me. As I said, this session should be interactive and it will be more enjoyable if you wish. So then what is a fault stripping? Which devices will see this concept are R4 and R3. So this R3, R4 are basically those relays which are mounted on the feeder number 1. As I said, this is my feeder 1, this is my feeder 2. So this particular line is protected by two devices, R3 and R4. And so these two relays will see some fault stripping, because if we assume that these relays are overcurrent relays only and only, there is no other concept. So when the fault is incepted in feeder 2, so this SBDR will try to push the fault current as well. And in this process, these two relays R3, R4 will see huge amount of fault current. And then they will think that there is a fault in this feeder and they will try to open the circuit breaker present in this line. And this type of operation of the unnecessary tripping of the feeder, unnecessary stripping of the healthy feeder is known as fault stripping. So this R3, R4 relays are going to see the fault stripping concept. And blinding protection means the last concept, as I said with all of you, R1 and R6, this R1 and R6, these two relays will see the blinding protection. Why? Because for this fault point, the grid will contribute some current, and this SBDR also will contribute some current, IBDR also will try to contribute some current. So as a result, the fault contribution from the grid side diminishes. From the grid side, the fault current magnitude reduces. So therefore, the relay which is present here R1, it will see a very less amount of current, and as if it will not trip, that kind of situation arise. So in our laboratory, we have developed some techniques. I'll just share with all of you. some adaptive protection schemes we have developed for microgrid environment. So first of all, let us understand what is the meaning of adaptive protection. See, as I said, in smart grid and microgrid system, this is one of the concept I'm explaining, protection. There are so many concepts, like so many issues, like stability issues. You have developing the control strategy for the inverter converters, like DC-DC converter, which is present in solar, the inverters which are present in wind system and solar system, or battery system. We have to develop adaptive control strategy. So strategies are also work out anymore. So similarly, we are also proposing adaptive protection schemes. Okay.
Madam, 1 minute, madam. Madam, 1 minute, I will mute these participants. This is Satya.
Yeah, am I audible? Yeah. So, that means in this case, what will happen? What will happen that the dynamics? I mean here this adaptive protection scheme. Sorry, the adaptive protection schemes what we have developed is that we are trying to adaptive means if any change occurs inside the microgrid, any change is any change is present inside the microgrid environment, so the protection strategy will adapt. It will just change its settings accordingly, so that the on any fault which is incepted inside the microgrid is not going to be undetected. So everything will be taken care. So adaptive, for one example, I'll tell you, the first adaptiveness comes from the intermittent nature of the renewable sources, because the solar, throughout the day in the solar based renewable sources, the solar irradiance changes. Sometimes in the morning the irradiance level is very low, then lunch hour it will just be high, then again it will come back, and then the evening hour it will again slow down. So in this process, the irradiance level goes on decreasing. Okay, so therefore, I mean, if it is a rainy day, if it is a foggy day, so that it depends on the power generation also varies. So in that sense, the contribution of the fault current accordingly also changes. So this intermittent, and similarly for a wind system also, like wind speed varies like 2 meter per second, 6 meter per second. It goes highest like 12 meter per second, 60 meter per second. So if the wind speed varies, then the generation also accordingly varies, and the power driving process also varies. So in that way, you can say, let us say in some process the renewable sources are present, and some cases it's not present. Now, these are some of the scenarios I'm just sharing with you. So in this process, maybe one battery is out of order and the battery is not working, and one renewable source is absent or present. One line is outage. So these are some of the, there is a magnitude. So in that sense, impedance. So in the whole network, I'm talking in terms of the power. I'm not going in the control strategy part, or I'm not going to the topology of the inverters. Just I'm within the power domain. Okay, so this, in that sense, those changed scenarios, right? So those changed scenarios should be taken care inside the protection scheme. So then what will happen? Suppose, for example, my setting of the relay, overcurrent relay is 2 ampere. But suddenly I could see that the current magnitude has been changed to 3 ampere. So that means if I'll just trigger my relay decision based on 2 ampere, now it will be maloperated. And as a result, something may happen wrong within my network. So it should be adapted. It should come to 3 ampere, not 2 ampere. So that is what is the adaptiveness. For example, I'm just saying. So in this process, so we have to take care, and every time the technique should be ready to take proper decision. So we have proposed one microgrid control center. Basically, there are so many process how to present. See, so now the researchers, they are just avoiding this the relays concept. They are trying to put here some intelligent electronic devices, IDs, at the two terminals of the lines, and from there they are sensing the data and they are sending to a central control operator. Okay, so the central control operator, it will take all the decision, whether the line is, which line is, where is the fault, which circuit breaker is going to open, which renewable source is going to reconnected, connected, whatever. So everything. So this kind of system, you know, we call it as distribution system management. You can write it distribution system management, DSM. So under this DSM, distribution system management system, DMS sometimes we call also distribution management system. So under DMS, so many key components comes. The first one is operation, management, stability issues, load flow analysis, everything. It's a kind of a computing center. So in the computing center, all components are given equal importance. Like one operator will handle only the load flow analysis part. Another operator will handle the RTU status through the SCADA vision, through the SCADA process. One more operator will take care of the protection issues, the adaptive protection schemes which are running within the controller. And one more person who will be taking care reconfiguration status of the circuit. So reconfiguration means sometimes the tie lines which are present inside the distribution network, they are just reconnect and disconnect to just bypass the power. Suppose one line is off, so however some loads are going to be get some supply, the tie line should be put on and it should be on, so that power can be diverted through that line for the time being, and again it can be disconnected later on when the line is in service. So reconfiguration of the system, and some more other like virtual inertia concept, virtual harmonics concept, so many things, outage management, restoration management. So slowly we are just moving towards this domain. So hopefully in the near future we'll have a full-phased DMS system in hydrology. So that means what I'm trying to say, that a central control center can handle all the uncertainties, difficulties which are going to be challenges which are going to be faced inside a small microgrid system or small microgrid smart grid system. So we have tried to test this knowledge within our laboratory. Okay, so as a issues I say to all of you, those issues we have handled by providing one adaptive protection challenge. And this is one concept. One more concept also that the researchers they're adopting nowadays is that distributed control centers. So not necessarily we'll have a single central control strategy. We may have distributed control strategies, control like software. One control center. Near to my IBDR, there will be one control center. Okay. So what means, what is the meaning of that? So we have distributed the central control operator stations, we have distributed at different substations. So if what is the demerit of the main control centers? That if any one of the component fails, then we cannot control the other centers. But however, in case of your distributed control centers, if anyone fails, other center can help it. So the third one also we call it as coordinated operation of the distributed control centers, right? Like this. Okay, this is a kind of improvement movement, you can say movement towards the vision of developing the adaptive control centers. But remember, in our technique to give this adaptive protection scheme, it is very essential to know the whether the grid is connected or the grid is disconnected. That is very essential. So this process of knowing whether the grid is connected or disconnected, this process is known as islanding detection. So very small things I'll just explain on this island detection technique, and then I'll go back to the adaptive protection schemes, and then we'll wind up. So now islanding, the mode of operation, why this is essential, let me tell you in this light. Because if you do, first of all, our control center should know whether my main grid is present or not, whether my microgrid is connected to the grid or not. That the control center operator should know, because accordingly the settings of the relay also changes. The protection settings also changes. As I said, there are so many sections. Like you have stability section, load flow sections, protection section, you have outage management section, your restoration section. In every section, wire control section, voltage control section, frequency control section. So every section should be informed whether the microgrid is connected to the main grid or not. Therefore, it is a very essential component of the microgrid or smart grid system islanding detection. And this kind of islanding detection technique is known as, maybe it is an intentional islanding detection technique or an unintentional islanding detection technique. Okay. So, shall we give some 5 minutes rest, sir? Or I'll continue, sir. 5 minutes break we need. Then I'll continue. Sir. Sarvanam, sir.
You can. Yes.
Yeah, I'll continue up to what time? After that, 12. Right?
You can take up to 12:30 like that, man. 12.
Okay.
12:30.
Okay. So I'm taking 5 minutes break. Okay.
Okay, man.
Dear participants, it's kind of 5 minutes break. I will start for the 11:30.
Okay, sir.
Okay, madam. It's
So let us start.
Welcome
Let
back
us start.
to session, madam.
So, yeah. Yes, sir. Are you saying something?
No, madam. Welcome back to session.
No, it's okay. Thank you.
Okay, madam.
So this one, the proposed, as I said, we may have different topology, different types of ways out how to have this proposed adaptive schemes. As I said, we may have a central adaptive scheme, central operating station. We may have decentralized, distributed. Okay, so decentralized and distributed almost remain same, except their communication channels are different. And then we may have a localized control centers, and we may have coordinated distributed centers. So depending on that, we may opt any of it, any of the fashion. Now in this our research propose techniques, what we did, we have taken a centralized operating station. Okay, so this is actually the microgrid control center. This is the operators will sit here, and there they will take all the decisions. And for this purpose, the light color lines, the dark lines are the power flow lines, and the light color lines you can see here, my cursors are moving. So those are actually communication lines. Okay, so in the smart grid or microgrid, as I said in one of the PPTs, is it possible that every microgrid will act like a smart grid? Yes, it is possible if we can make it automated in nature. I mean, we have a very dedicated IT sector, infrastructure, communication has to just, and the system will just move automatically according to the requirements. Okay, so this is known as automated smart grid microgrid system, smart microgrid system. Now, this is how the control center looks like, microgrid with control center. And at this control center, whatever I'll talk to you now onwards, everything runs within that control center. The control center is nothing. It's a big screen will be there, and there will be a controller like which can be from a company like NI National Instruments, or it may be from DSpace, or it may be from FPGA based controller. So any type of controller, that controller will receive every time the voltage current signals, and it will just try to calculate all the information. See, not necessarily you may ask me that the control center is far away from different substations, how the voltage current signals are going to be sent. Yes, it is now, it is quite possible through the wireless medium also. Okay, so there is a different topic also, communication infrastructure, which is designed, and research is going on by many researchers, the communication technology for smart grid environment. So this mode of operation at the control center is essential, because if I do not know the control center and the grid connected mode of operation, or it is in islanded mode, I mean the grid is absent. Okay, so my accordingly the technology, the proposed technique one is dedicated, or setting one is dedicated for grid connected mode of operation. Setting two is for islanded mode of operation. Understand? So if I don't know whether my grid is connected or disconnected, so the controller cannot take any decision. So this process of knowing the grid connected or grid disconnected is known as islanded detection, islanding detection. So this see here, this circuit here, switch is grid control center, and here this switch is off, and this is also going to be sent to the microcontroller. So when the switch is off, the grid is disconnected. The whole microgrid is going to be operate in the islanded mode. So this is one of the forum why I'm talking this mode of operation is essential as and also the distribution grid protection reconfiguration is also essential because this is a real thought process. This is actually International Smart Grid Action Network. You can type this one also, it will come. It is international level one smart grid forum, and under this there is one more forum, Smart Grid International Research Facility Network. Means in the globally we have a forum which takes care of every action of the smart grid. So even what kind of research is going on in every country, like in India, Europe, Germany, Canada, US, Australia, like other Iran, South Africa. So whatever the countries, developed nations or I mean developing or developed nations. So time to time they review the status. So under that, see, for anything, whatever is happening, the research is very essential. Therefore, in every company, they have kept one section, R&D section. So R&D means research and development section. If there is no research, means there is no development for the country. Okay, so under this Smart Grid Action Network forum, one more forum is Smart Grid International Research Facility Forum network. Okay, and under this ISGAN, this one International is ISGAN stands for International Smart Grid Action Network. Okay, so under this International Smart Grid Action Network, and there are so many annexures. So under annexure 5, this comes Smart Grid International Research Facility Network. So you think how big it is. So they have you can read also this articles are available in IEEE. So ISN Annex 5 under this research forum comes, and again under this annexure 5, power systems testing PST comes. And again under this PST, the distribution grid protection and reconfiguration part comes. So that means why I have shown this PPT to all of you. What I am talking, the research things, whether this is recommended by industry, by the IEEE standard benches, or by global forum or not. See, whenever we are starting any research, whether it has a very meaningful thing or not, it is feasible or not, whether it is a desirable field or not. If not, so we should not continue the research because there is no thirst, there is no thirstiness regarding that particular field. There is no need for that field. So it is a need. I am just talking to you. It is a need, real need for the researchers, for the society. So therefore, these people, they thought that distribution grid protection reconfiguration is one of the major area under the Smart Grid Action Network. And out of it, again, one more function I found that the inverter which are used in the, see, this IBDR has an inverter which converts DC to AC. It is a smart inverter. What's the meaning of smart inverter? It will quickly say that whether my IBDR is connected with the grid supply or not, whether my IBDR is connected to the network or not. It will just quickly tell you. Why? Because why it is essential to know this status? Why the smart inverter function is necessary? Because due to that, when the IBDR is connected to the grid is connected, its control strategy will be something else. And when the grid is off, the control strategy will be something else. Okay, why? Because when the grid is connected, mostly the inverter's control strategy, they takes the reference voltage frequency from the grid. When the grid is disconnected, their frequency and voltage will be something different, and their control strategy should switch over. So they should know the status of the main grid. That is one aspect. And therefore, this anti-aliasing effect, anti-aliasing support with the grid support function should be enabled within the inverter of the renewable sources. Okay, so there are so many things I just told you why this mode of operation is essential. And even then, if this unintentional islanding is not detected, so many issues are going to come. The first one is out of phase reclosing. Suppose this is a grid which is disconnected, and this is your microgrid. And when this microgrid is disconnected from the main grid, what happens? The frequency of this particular microgrid changes. Why? Because when it is disconnected, the load and power generation doesn't match. It may also happen loads are generation basically due to the renewable sources. Okay, so this delta P delta Q mismatch in active reactive power may lead the variation in the voltage and frequency. So when we are going to reclose again the switch, for synchronizing process, this is known as synchronization process. So in that case, the voltage and frequency of both the grids should remain constant. So this is a out of phase reclosing and degradation power quality, obviously, because when it is disconnected, there is a change in voltage and frequency. And grid protection interference. Already I discussed with all of you that during the grid connected mode, the current magnitude is something else. During islanded mode, the current magnitude is something else. So the relays are going to be, the settings are going to be changed time to time. Okay. And inverter control mode switching, already I said in the previous slide, because during grid connected mode, the inverter of the renewable sources, it will take the reference of the voltage frequency from the grid side. And when the grid is absent, so it has to switch over to another control strategy. And equipment damage, why this equipment damage is written? Because like if you have some induction motor type of loads, so if the frequency voltage varies, so there is a change in the torsion speed of the rotor, so that may create some problem to the loads, that kind of loads. And threatens to the personal crew safety. Why? Suppose, let us say you have some loads at this grid bus, okay, and when this grid is off, the people know that the grid is not anymore, so they are just on the field, whatever, casual they are moving. But however, they don't know that this microgrid, which is actually inside microgrid, renewable sources are present. Those renewable sources may supply current to this bus. The person who are, the crew person who are working, they may get some shock. And over that, I'll just tell you another point. The overvoltage may also occur due to the transients. Overvoltage may rise due to a lot of rapid loss of loads. And if you don't have adequate grounding system, ground source is not present in the island, okay, a ground fault can result in the voltage exceed of 173% of the unfaulted phases. So these over voltages are also serious issue. On this topic, some people can also go ahead and research. We are also trying to more investigate, not in a theoretical aspect, but in a very practical aspect. Okay. So these are some of the power quality issues already said. Protection already I have discussed with you. So there's so many techniques, conventional techniques are available, like rate of change of frequency, phase jump detection, power change, voltage change. But I'll not go in detail of this because I have to go one more new technique in this particular session. So these are very conventional techniques, and I can say this much, that these techniques are actually running inside the center, control center. The operator is looking what other techniques are running, and these techniques fail for zero power mismatch condition. Zero power mismatch means when this microgrid is disconnected from the main grid, not necessarily, sometimes what happens, the power, the load which are present inside the islanded microgrid may be equal to the power generated by the renewable source. And in that case, the power generated and the load present, active power, reactive power mismatch may be zero. So during that, the voltage and frequency variations are very less. So this is known as zero power mismatch. So during those periods, the rate of change of frequency, voltage, almost angle, so those, fail, right? So for that, we have developed one new technique that is known as new rate of change of superimposed sequence impedance based technique. So we thought of during our research process with the research scholar, that why not we will jump, why will not jump to some other kind of impedance based technique, which where when the grid is disconnected, of course the impedance of the circuit changes because one source is disconnected, right? So rest of the network impedance are going to be changed. So therefore we thought of just grabbing one new technique which is known as superimposed based sequence component based technique. So what is the superimposed negative? Why again negative sequence? Because let me tell you, when the fault occurs, you have you have negative sequence component present, positive sequence, zero sequence. So why negative sequence we have targeted here? The two things I want to share with all of you, because the negative sequence based technique is not affected by load change. Remember this, because in a distribution network, more or less, it is actually unbalanced in nature. Why? Because in distribution network, per phase loads are not equal. Let us say if phase A is having some load, phase B has some loads, phase C has something other loads. So when the loading of each phase are different, so obviously, you know, unbalancing is there before the fault situation also. So we have exploited that situation. So negative sequence is also negative sequence current and voltage to some extent is present before the islanding scenario. So therefore it is quite easy for us to calculate the pre-disturbance, pre-islanding scenario negative sequence impedance, that is known as Z2P. And this Z2P is nothing, the Z2P means V2P divided by I2P at the renewable source terminal. We are calculating these parameters at the renewable source terminal. Now, after islanding, what we'll do? We'll also calculate V2 island and I2 island. Again, we'll calculate Z2 island. So, difference between these two is known as superimposed component. So, superimposed means what is the present situation and what was the previous situation. Just you subtract it, and that difference is nothing, the superimposed sequence impedance. So this is how we have calculated delta Z2. The superimposed negative sequence impedance is known as Z2 post minus Z2 pre. So we have calculated this component and we have taken some threshold, of course. In our technique, the major drawback is the threshold setting, but the major advantage is we have overcome the NDZ problem. So what we did at the terminal of the renewable sources, we have calculated the pre and post voltage current signals at a sampling frequency of 1 kilohertz, and phasor estimated by LES technique, means least error square based technique. This is least error square based technique is one of the technique which is used for phasor estimation of the voltage, digitalized instantaneous voltage and current signals, and then estimation of the pre and post negative sequence voltage and current from there, because LES will calculate the phasors VA, VB, VC, II, BIC phasors, and from phasors we have to calculate the negative sequence components like V2 is equal to VA plus A, VB plus A square, VC 1/3. Okay, so after knowing this V2 pre, I2 pre, V2 for post and I2 post, so easily we can calculate the ratio and calculate J2 pre and J2 post. Then by taking this equation, we can calculate the superimposed impedance. And then we took one more parameter after this, rate of change of uh, uh, sequence, negative sequence impedance. Okay, so that means after delta 2 is calculated, so just we will calculate the what is the subsequent change of delta Z2 with respect to subsequent change in time. So that is known as rate of change. So after this, we will decide one threshold. If it crosses that ROCSI and crosses a certain threshold, then we will declare it's an islanding scenario or on non-islanding. Islanding means the grid is not connected, and non-islanding means the grid is present, but some other phenomena like when DG disconnected, fault is there, load switching, line switching. So those are actually non-islanding scenario. So that time this technique should remain silent. Okay. So this is how we have developed this technique, and this is the LMS technique, least error square based technique. Due to time constraint, I cannot explain this. So this is our technique. To evaluate the performance of this technique, we have taken one microgrid system we have developed through RSCAR software. We have a laboratory called as Real-Time Digital Simulation Laboratory, RTDS, Real-Time Digital Simulation Platform. The device name is RTDS. Around we have 6 racks, and these racks This device is purchased from Canada, Manitoba institutions, around 10 crores cost. So luckily, fortunately, we got an institute has funded that device, and inside that device we can simulate any kind of smart grid environment, microgrid environment. Inside that we have solar, wind system, battery, we have diesel generators, we have synchronous generators. Every components of the smart grid microgrid systems are available. Storage devices. So like this is a IEEE 13 bus system, and the same system we have developed inside the RS card environment within the RTDS. It looks like this. So after that, the IEEE 13 bus system is a system. Therefore, we have developed. Okay, even we have also developed IITR distribution network, where we have a rooftop mounted 2 megawatt of solar penetration also. That also we have developed. So these are some of the results you can see here. So minus this negative means APM stands for active power mismatch, plus means plus APM, and so this is actually the negative voltage, negative current we measured, and this is how see negative impedance, and this is your SNSI, and this is rate of change of SNSI. So this rate of change of SNSI you see very clearly mentioned. It crosses the threshold. When this crosses threshold, so the all these calculations are at the end of this at the terminal of the renewable source. When this is crosses like this, the symbol is like this. Suddenly, all these informations are informed to the control center, and the control center will come to know that the grid is absent. Okay. So these are some of the worst cases we have considered, and this is test for IEEE 34 bus tie lines. See, we have simulated IEEE 13 bus system as well as the IEEE 34 bus system. Basically, when we do research, we have to test the techniques in a very standard benchmark IEEE system. Otherwise, the technique is not going to be accepted. If we take a very simple network, schematic network, the reviewers, the chief editor may not accept it. So we have to always prove with the standardized IEEE 34 bus, 33, 132, 13 bus, like that. So in this system also we have taken a grid. Okay, and we have this feeders, tie lines. I said once to you, tie lines helps in supplying, getting a alternate path to get the power supply to the loads. And this is here we have one solar. This is PV system. This is also one more PV system. This is one synchronous generator system. This is one DFID system. So we have taken almost all type of renewable, and we have tested this technique. And you can see here in the tabular form I have shown, previously I have shown in graphical form. So this is a rate of change of SNI values. See, so it is when it is crosses out this threshold, so it will declare that the grid is not present anymore. So this thing also we have implemented in the HIL test bed. So HIL test bed means what? Hardware in loop test bed. So the whole system microgrid will run within this RTDS, and from here we will take the analog signal through GTAO. GTAO means Giga Transfer Analog Output Card. It will come to outside, and this is our controller where the technique runs. And again from here the technique will be executed, and then the output signal will be sent to the back through the GTAI card, Giga Transfer Analog Input Card. So this total is a closed loop kind of thing. This is actually RTDS, what I was talking to you. Have RS. Okay, so this whole setup is known as hardware in test bed. So whether we will go ahead or we'll stop here. So I hope that I should take some questions from the participants. That will be good. Is it okay, sir?
Yes, madam. It's very nice, madam. They nicely explained what are the new equipment also available in the smart grid. The faculty members are also aware of this new equipment.
It will be permitted sometimes, some other time also I have more concepts further also. Research oriented. I can share with all of you, but this is just initiation with all of you regarding the smart grid production challenges. And see, actually, honestly speaking, many many students who are working with me, they are working towards the protection of AC microgrid, DC microgrid, hybrid AC-DC microgrid with the presence of battery. So hopefully in future I'll be in touch with you, sir, and then we can do all the sort of work. You can collect the questions, sir.
Sure. And dear participants, are you having any queries? Just unmute your audio and directly interact with our resource person. This is the very good opportunity for you. Mr. Ravinder, sir?
Yes, sir.
Mr. Ravinder, first you say what of thanks to our resource person. After then, the participants are willing to interact with our resource persons.
Okay, okay.
Okay, thanks, Sir Ravinder.
It's my privilege to give the out of thanks for today's session. I would like to thank Dr. Premalata Jain. Ma'am explained about the technique like novel protection scheme for the smart grid, and ma'am explained different techniques in that blending of protection in microgrid, adaptive protection schemes, and different modes of operation like grid connected island modes, and issues with the unintended island detections and islanding detection techniques. And later madam explained about RTDS software and how it will be implemented with hardware kits and some thrust areas in the protection scheme. Thank you, madam, for giving valuable time with us and a part of this STTP.
Yeah, thank you so much. Thank you, sir. If any questions, I'll be very happy
Madam,
to answer.
Yes, madam. One student raised their hand. Their name is Rana Afrin. Turn on.
Yeah, you can type in the chat box also. I can read and
Rana Afrin. Yes.
Yes. Good afternoon, madam.
Yeah.
Ma'am, I want to know some personal thing. Is IIT Kanpur or IIT Roorkee is conducting any postdoctoral programs?
Yeah. We have postdoctoral programs facility. Like you can write one project title or topic, and we have to choose the supervisor and not supervisor, kind of mentor. So we have two facilities. One is a institute level PDF, and one is DST based PDF. We call it as NPDF. NPDF means national level PDF, and this institute level IPDF, institute level PDF. So both the cases there will be scrutiny and interview, and then you'll get the money. Like we have that facility, 60,000 per month. If I'm not wrong, that facility is there.
Okay, thank you, ma'am.
Thank you for attending.
Any other participants? Please interact with our resource persons.
Yeah. So any questions from the participants? I'll be happy to answer. Yeah.
Ma'am, can you provide PPT in WhatsApp group?
Yes. I can provide. I'll provide that. Okay.
So any other participants having any queries, to unmute your audio, otherwise to wind up the session. Okay, madam, it's thank you. I think it's all the participants are satisfied. You are very good lectures. This reason none of them not ask any questions. You explained it's very clear, and it's discussed a lot of practical things and practical issues also you discussed this day. It's once again I thank to accept our invitation and delivering a very nice and excellent lecture to the participants. Thanks once again, madam. Thank you.
Yeah, thank you so much. Thank you, sir, for your kind. I need your cooperation like this, and I'll be there. No issue. And I'm really thankful to the participants specifically. They have joined this session, and they gave me some encouragement to present in front of them. So I'm really happy for them. Thank you so much. So thank you so much. Yeah. So I leave, sir, now.
Yes, madam. You can leave, madam.
Thank you so much. Thank you so much.
Dear participants, the feedback link posted in the posted only for the chat box. It's try to complete the feedback link before 1 p.m. today.
Sir, can I leave?
Yes, sir. Sir, 1 minute. I will post this feedback link.
Yes, sir.
1 minute. Wait for 1 minute. I will post this one.
Okay, sir, I posted now.
Okay, it's already posted.
Sir, I'm unable to open the feedback link, sir.
Okay, it's madam. Try for another one time, madam. Just now I posted another one, madam. I will check. Yes, it's
Sir,
opening,
yesterday
madam.
I'm facing the same problem.
Network having its in this.
No, I'm on Wi-Fi connection only, sir.
Okay. What problem arises, madam?
I'm unable to open your link, sir.
Okay, to mention
Is
that.
it necessary, sir?
Yes,
Compulsory
madam.
we need.
Compulsory the feedback is mandatory. Otherwise, how will give the certificate? Yes, just now it's open it. I will, even though I will send the screenshot for your reference also.
Okay, sir. Thank you.
Okay, it's opening, madam. Just now, this is for you. Check in chat box. Madam, if possible, you send the text message to my number. Just it's note down my number 9493.
Okay, sir. 1 minute.
Okay.
9493
48